Hello, everyone. I hope you had a great lunch. Lunch was beautiful. And welcome to this just after lunch session about continuous profiling. Not the best topic to talk about after lunch, but hope you will enjoy it. So in the next 45 minutes or so, we'll talk about what profiling is, what is continuous profiling, what continuous mean in the sense of profiling, what are the tools that we can use, why and why not we should or we could probably use continuous profiling. But before that, the boring part, a little bit of intro. I'm Mohammed. I work for an audio streaming company called Spotify. I'm also a Google developer expert, GDE, for cloud technologies. Enough about that. How many of you have been on call before? Okay, so you know what I mean. And you know how hard it is to wake up in the middle of the night when you get an alert, trying to figure out what's happening and trying to bring the system back up and running. And for the rest, on-call basically is you get paged whatever in the day or the night, basically, to get to fix an issue within the system. And God knows how hard it is if you need to wake up at 3 a.m. in the morning without knowing what's happening, especially if the system is another cheap system. But yeah. But that's image generated by DALL-E. I have a couple of these in the presentation because just as fun. Image generation now, it's a lot more easier. But that's how exactly probably I look, waking up in the middle of the night trying to figure out what's happening. And before diving into profiling is, probably going a little bit into history and figuring out how complex our architecture became. In the 90s, this is how the majority of architecture looked like. It was simple flow between the client and service. All the components of the system packaged together in a single executable and deployed into a server. The problem with that is when we need to scale become an issue, and then we started to stumble upon a lot of issues. And then to scale, we started to split our system into multiple small components. And in the beginning of the 21st century, we started talking about service-oriented architecture. And we started to split the system into small components, and those components collaborated together either to pass simple data or to achieve some functionality. And in order to ensure connectivity between those services, we started to use smart pipes in terms of ESBs and MQs. But even with that, MQs and ESBs, whoever worked with that, was, from an organizational point of view, hard to put in place. And the promise that they promised, basically, was not able to make it concrete in practice. So we ended up with organizational challenges as well. And then microservices came in 2010, and we even break our services even more finer. And we move it toward dump pipes and decentralized communication, making everything smaller. But then we started to stumble upon other type of issues. And the truth is, decentralized communication follows Murphy's law, which says that anything that can go wrong will eventually go wrong. The moment when we split our application into smaller services, the thing that monolithic architecture guarantees are no longer true. Services now no longer start to stop in the same time in a predictable manner. There are a lot of issues that can go wrong when we move those in-memory or in-process call to RPC and network. And some of those issues are observing interaction between those services. Previously, we had simple flow of communication. Now with those multiple services, observing those interactions is hard, especially on the network, and understanding what's happening behind the scenes, why this service is slow, why this service actually returned an error, and so on and so forth. Traffic management also become a lot more harder, complex to do. Things like A/B testing, canary deployment, traffic management is also become more and more challenging to perform with those loosely coupled components. Security communications. Previously, had one server put whatever knowledge you have and whatever expertise into one place. Now with this decentralized communication, we come up with what we call MTLS, which is like both ways security between the client and the service, between both your services. So more concepts are phased out or resurfaced to secure the communication between those microservices. But it's just to say it's becoming a lot more harder. And also, because we have more services that are communicating through network, we have communication failures because it's network. Nothing is guaranteed. And then also we have timeouts when a service is slow, and probably there's running out of resources and so on and so forth. And for anything that's related with the risk management, we bring the Johari window framework, which is basically, it splits the risks into 4 categories: known knowns, unknown unknowns, known unknowns, and unknown unknowns. And it's valid for any practice. But in software engineering, we'll focus mainly on the 3 windows here. So the first one is known knowns. And the context of software engineering is the things that we know that how our system is behaving, basically. We know that if a request is malformed, the request will basically fail because we have validation in it, right? Because that's standard practice. We know that if you divide by 0, then they would trigger an exception, an arithmetic exception, right? Because that's not valid. So there are things that we know that if you call a function in a null object, then that will trigger a null pointer exception. So those are the fundamentals, absolute truth that we know about our system. And then we have the little bit tricky part, which is the known unknowns. So we know some issue is happening, but it's still unknown in why actually it's happening. And an example for that is a slow request in some path. So we know that users are actually have degraded performance because there is some slowness in in the request, but we don't know yet why. But it says at least it's aware. We're aware of there's issue happening somewhere. And then we have the unknown unknowns. And that's the source of most big outages. The things that we don't know and we don't notice until they become big outages. Things about memory leak, security vulnerabilities and stuff, where they are kind of getting compiled until they bring our system actually down. And for most of these, up until recently, we focused on the 3 pillars of observability. And then again, this image was shared by Dali, and it sucks when it comes to errors. But yeah, forget the spelling mistakes there, and just focus on the things that are there. We use it to what we call the 3 pillars of observability for a long period of time, in terms of logs, metrics, and traces. Logs are simply time-stamped record of events. If something happened, we log it, why it actually happened, and help us to understand what we call the why. It helps a lot to understand why the user is actually, or our users are facing such issues, and what a specific user is having specific issues, what a specific event was triggered, and why. So we try to answer the why question, why this issue actually happened. And they are textual, and they try to provide as much information about our system behavior and help us to understand why we're facing such issues and allow to explore some of the issues that we have. They're easy to set up. If we believe that something is lacking, we go there, we add some lines of code, and sometimes we abuse the logs, and we log basically everything and help us to understand why something is actually going wrong. And then we have also metrics. And metrics are numerical values that tell us how the health of our system is. Think of it as memory consumption, CPU, latency, and so on and so forth. So basically, they give us a micro overview of how the health of our system is. They are quantitative, so we gather them, we collect them, we analyze them, and then we output them into graphs. And then they are more focused on KPIs, key performance indicators, like how much CPU my how much CPU application is consuming, how much memory is it actually using, how much is the latency, and so forth and back. And then if there is a trend, like if there is a peak in CPU, we know that, oh, at that point of time, there is a peak in CPU, and we can go back and understand why this is actually happening. And the data that we collect and gather is actually real time and describe the health of the system at that specific moment. And with the rise of decentralized communication and microservices, we added another pillar, which is traces. And traces helps to follow the request journey through all our internal systems. It's basically tell us from the moment the request entered our parameter until it left, the path it took, and if there is some bottleneck somewhere, some latency issue, some error, it can tell us where it's actually this bottleneck is. And it helped diagnose hello? It helped diagnose bottlenecks and latency issues and faults if we introduced them. And then I was super proud sharing the image generated by DALL-E about the pillars and so on and so forth. And Jonathan Ivanov, which is a great friend, and he works, probably still works in Pivotal, now Broadcom. He's one of the developers of Micrometer. I'm not sure if you know it, but it's a great tool, especially in the Spring ecosystem. But it's too much into, he's very experienced in when it comes to monitoring and observability and so on. And he told me that observability should not be defined with pillars, which is completely true. And the amount of pillars, no matter the amount of pillars we have, it cannot tell the whole picture. And that is true. Because those pillars tell us basically the macro level of our system, like what's actually happening. But then we're still lacking some pieces to understand actually being more proactive. And no pillar alone will help us to understand how our system is behaving, and the best would be basically to reuse all those components and actually to understand how the system as a whole actually behave. So pillars is probably not the right analogy to do here, but just for the sake of understanding. So I mentioned that we use metrics, logs, and traces to understand the Johari framework, right? But they just answer the known knowns and known unknowns issue. Logs excels in understanding known knowns. If an issue is happening, if a null pointer is happening, you can go to the logs, check the trace, struct trace, and understand with actually the null pointer actually happened, and go back and try to understand what's happening. If you have a latency spike or a CPU issue, you mix and match all those, the three pillars basically, and try to understand what's happening. A mix of logs with a mix of traces to understand what this latency is actually happening, and go back and try to understand what's happening. But then unknown unknowns, it's still lacking. Actually being proactive in terms of what's actually causing this memory leak. Being proactive about it, understanding why the heap size actually growing and growing without me understanding why. And the three observability pillars actually don't answer it very well. So the promise of profiling is being more, giving us more understanding and more tools to understand the unknown unknowns, and giving micro-level understanding of the health of our system. And to understand what three pillars of observability compare to profiling, the analogy that I always gave is that the three pillars of observability gave us micro-level understanding of our application, and similar to the vital signs of our body, like temperature and the signs that leads to basically what we are sick. So it gives a micro level of understanding of following your heart rate, your blood pressure, and so on and so forth. Profiling is actually the X-ray. So it gives you the internal function of the body and understanding of why this actually happened. What are the different root causes that leads to probably having a raised temperature or a headache or something. And there are different kinds of profiling that we use for different usage. Like CPU profiling try to answer the question of what's consuming much of my CPU, what is consuming much of the CPU, and it's mainly focusing on throughput. What function, method, something that is using all that CPU, and why, and what it's using it for. Wall clock profiling, it's also focusing on the CPU usage, but more the length of it, how long, why this method is taking so long. So CPU profiling is focusing on throughput, wall clock profiling is focusing on latency. Allocation profiling is trying to answer the question of what's causing this allocation pressure and why. So be it memory, be it the threads and the heap, and so on and so forth. The lock, we give it a different name in the lock profiling thread halt stop the war thing. Trying to answer the question of why my thread didn't execute at this specific moment and why. It's focusing on the threads, similar to allocation profiling, but it's focused more on giving context to why this thread function didn't execute at the right time and why it actually failed. And heap profiling is obviously focusing on the heap memory, what's causing all of this heap memory to be consumed, why is causing this, why is there an increase in the heap memory, is there a memory leak somehow or somewhat, and then I try to react to that. And then we have two types of profiling, what we call the traditional profiling up until now. And those were basically either desktop tools or we need some tools actually to run it. So we need a user space program that perform the profiling. And those traditional profiling tools were costly to operate, costly not in terms of how much they cost, but costly in terms of how late overhead they add to the application. And that's why we did not add them to production, and we limited ourselves to pro-production environments. So either local dev machine, you add a profiling tool trying to understand what's happening. If there is a case of memory leak, understand the tool, have some graphics, and try to follow. Probably testing or dev environment in the server, but we're limited to before production. And so we had limited visibility because it was not into production. If the issue is happening actually in production, we're in the blind. And it has a big overhead in terms of latency and then of resources because it's another application, another thread, a couple of threads running in your production system. So the impact is big. And also there was what we call missing symbols. And symbols is, so if a method is running in your CPU, the CPU just executes the binary calls, right? It doesn't need this method is called get me price or get prices, right? We need it for us in the profiling to understand what method is actually using this allocating or using the CPU or using this threads. Think of it as your contact numbers. If you have a WhatsApp group, you can't distinguish the people sending what by the numbers. You need to have them names. So symbols is basically that, but from a program level. So what program is executed in this time in CPU, and that's why we need to get the CPU representation because the machine doesn't need name. It excels in execution, whatever, but we needed to understand what's actually, which method, which piece of code is actually running. So that was traditional profiling. And just long, which will give the keynote of tonight, says, production is the happiest place on earth. That's where the action happens. That's where the users get to our servers to get value from our application. And development is very different than production. Issues happens in production and not in development. So the more we are capable of getting the information for production, the more we understand our system. It's like that's where the action happens, and that's where generally the issues actually happens. And then enters continuous profiling. And continuous profiling, it's not new, it's an old age techniques, but continuous added dynamic time-oriented variable to it. It's basically, we are continuously profiling our application no matter what time it is, rather than in specific periods when an incident happens and when there is like an issue in our applications. It has a low overhead, and that's why it's more production friendly. Generally, it's 1 to 2% overhead compared to other applications. They're headless. They basically run on your production environment and then send data to your system, and becoming more and more, getting more and more popularity, especially in the world of cloud native nowadays and microservices and so on. And I mentioned it's not new, because like the first paper that was shared on continuous profiling, and the term actually came from a 2010 old paper from Google engineers. And they said in this paper, that's a valid QR code if you want to like just to read the original paper, but it actually dictates or put the initial design of what continuous profiling actually is. And that the architecture that you put right there is the architecture that's been followed since today, until today in terms of designing and architecting a continuous profiling tool. The paper was shared in 2010, so we believe that it was used in Google for years before it could actually shared. And then, since then, especially in the rise of cloud-native era, there are more and more tools that are both open source and commercials that are advocating for continuous profiling and making the adoption of continuous profiling a lot more easier and a lot more seamless. Google made it part of their Google Cloud stuff. Amazon followed afterward. And then Datadog, which is one of the known in terms of monitoring. And then we started to see a lot of open source tools came. Pixie from the CNCF. Grafana has their own with Periscope. And then we're seeing a lot of tools that are coming. And in terms of architecture, is pretty straightforward, pretty simple. You need an agent that collects the data, that collects the profiling information and the sampling information. And for that, I have two choices. Is either to build our own agent, or use an agent that is already available, or instrument the app to send those profiling information. The choice is yours. Use it, do what fits your application, but generally using the agents that collects a variety of information is generally the way to go, unless you have a definite specific use cases to do it. And then when we send this data, we need a way to ingest it, clean it up, put symbols, clean up the profiles, and then send it to the profiles. And then the profile is the heartbeat and the core of the profiling architecture. It's what it tells what, and then puts all the intelligence and deciding on where to go with what. And then to understand what's actually happening, we need to add symbols. Again, think about it as the contact list in your information. It comes as numbers, and then you need to put symbols on what is called using much of my CPU. And then you get all the information, you need a way to store it. If you're thinking about long-term storage, some profilers or some tools doesn't care about it, depends on the application or depends on the usage, but then storage is an option if you want. And then we need a way to visualize all the information that we collected, and then we will have the front end. And generally, when we think about CPU performance, we think about flame graph, and this image is taken from CNCF Pixie, which is a cool tool from New Relic. I will talk about it in a few slides afterwards. And then the flow is pretty simple. What profiling information do I need to collect? And that's what the profiling piece trying to answer. And then when you get those profiling information, what do we need to do with them? So we collect the data, we clean it up, and we put it into a data analysis. So once we got this data, then we need to visualize it. We need to put it into a meaningful format. Collecting the data without processing it is useless, basically. So when we get the profiling information, we collected it, we analyzed it, and then we end up with visualization. That's actually the flow that is followed in all the continuous profiling tools or the profiling tools. It's basically these four main steps. You need to put an agent, that collect the data, send it to our profiling. That's basically where the magic actually happens, and then analyze the data to put it in a meaningful format, and then we visualize it to understand what's actually happening. There are different types and techniques to do profiling, and I will talk a little bit about 4. The sampling profiling is the very simple, very straightforward one. It's basically collecting data at a specific period of time. In terms of CPU is always running. We collect it at each 100 milliseconds, 200 milliseconds, and so on and so forth. So basically, getting those information, getting a sample, that's where the sampling profiler came from. We get a sample from the execution, memory, CPU, and so on. We collect that information and send it back. So we have time point that is collecting the information, and we send it to the profiler for more analysis. And then we had event-based profiling, and that's where an event that we are interested in actually happened. Could be an exception, could be a latency, could be a cache cleanup, could be anything. But it's an event trigger, then we collect the information to understand what's actually happening. And then instrumentation profilers, and that's where you insert profiler checkpoints into your code. So we're interested in understanding a specific piece of logic while it's actually taking a lot of time. You kind of add profiling information before and after to understand what is actually happening, and that helps you to gain a deeper understanding on what's happening into your code. It has a drawback that you need to modify the code and run it again, but it's still an option if you are interested in understanding, having more fine-tuned, fine-grained control over understanding of what's happening in your application. And then we'll have threshold profilers. And thresholds are, you're not interested in all the data that's happening, but understanding the outliers. And say, for example, a method that is taking more than 100 milliseconds, and when it's past that, you want to understand why it's actually happening, and then you collect all the outliers. Probably there is a database issue, probably there is some thread that is blocking the entire information. So we collect all the outliers or the necessary context, and then send it to profiler for better analysis. And then profiling, or continuous profiling, the same challenges actually are in both worlds, but it becomes more and more present because we are continuously collecting profiling information. The first one is symbolization. The tools put a lot of effort in making it more human-readable format, but it's still, especially if you're doing instrumented profiling, putting profiling information into your code, could be a challenging to symbolize it basically and have it in a human-readable format. So that could be one of the challenges that you face. Efficient data collection, from my experience, that's the hard part. It's to decide how much you want to keep the data. Profiling is very verbose, and the amount of data it generates is massive. And then deciding how long you want to keep the data could be a critical question that you need to answer. When you start, you're collecting the information, you're seeing your graph, it's all good, it's all happy. But then storage is cost, is money. Then how long you want to save this data, and how much compression you want, how much retention you want. That's some of the questions that you will need to answer. X-specific queries. Most of the tools offer a way to query the data. So putting it in a human-readable format or easy readable format can be challenging. The tools that I will show have their own query language, which makes it a lot more easier. Correlation with other signal types, that's really important. As I mentioned earlier, don't think of it as pillars, but think of it as a set of tools that mixing and matching would help you to understand better what's actually happening. Widespread adoption, that was true up until some point, but it's still valid. We're seeing a lot of adoptions from about continuous profiling. There's the big companies that are using it for obvious reasons, but also the entry point has came down because there's a lot of open source tools that can be used for free and a lot more easier to set up. So the adoption is gaining a lot of momentum. Accuracy and representative sampling, especially with sampling profiling, can be an issue. Because when you collect 100 milliseconds, you may, or within a cell, correction in samples at a center amount of threshold, that could give you a wrong view or a misleading view about the health of your system. Because like, what the threshold you put to collect the information? That's a question that you probably need to answer as well. One of the big motivations is actually cost saving. And this is a cool graph from Grafana that why we're saving costs with continuous profiling. So the more your system is running, the more resources it would need. And optimizing the performance of your application can lower the amount of resources it actually uses. So that's one of the keys that you can use in order to talk to someone about why continuous profiling is good, or what profiling in general is good, especially continuous profiling. So the complexity of this system grows with time. We take some shortcuts in order to deliver value and to make the product people happy, but then the performance of our application degrades over time because it's, in terms of needs more resources, needs more time to operate. It's in the green box in there.
Yeah, compared to top profiling, it looks not that.
So with that profile, it's up there. So the cost profiling is, so let's imagine that your application needs 4 CPUs, right? And it's full-time CPUs needs X amount of memory. You did continuous profiling. You understood that you can optimize this piece of code instead of taking X amount of time. It's now less, so it runs faster. Or it needs certain amount of memory. Now it can be used with less. So we are reducing the amount of CPU time that your functions or multiple functions needs, and reducing the amount of memory that your methods needs, basically. So reducing both the CPU and reducing both the memory make your application runs a less amount of CPU needed and less amount of memory. And then you can get back that amount of memory and CPU. And when we talk about resources, it means that money that you are paying either to your cloud provider or your servers. So you can either stack more components if you're on-premise. You can stack more components in the same data center or the same server, or pay less in terms of cloud virtual provider. So that's why the cost saving from profiling, that's the part that you are getting back by optimizing your code, both in terms of different metrics. Another one is better feedback loop. And that's basically a great win by having continuous profiling directly linked to production. If there is an issue, you get it straight out of it. So imagine you introduced a regression. You were working on a super good functionality that make your users happy. You ship it, the functionality is good. Running it on your computer, you didn't notice anything. The test passed, everything passed. And then when you release it to your production, you see that it's consuming more memory than it actually happened. There is a memory leak in one of the functions, one of the code changes that you introduced. So you follow it. You come after a couple of hours after deploy, or the next day you see there is heap size is actually growing. So there's a regression that is happening. If it keeps running and running and running, it actually could lead to an outage. So by having continuous profiling, we have a shorter feedback loop. We understand we can catch regressions if they are not non-functional regressions. We catch them, so we either roll back and try to understand what's actually happening, and then bring it back again, which is a great win. What's actually would happen with continuous profiling, so you have, in the morning, you bring your own coffee, and then you check what's happened since the last deployment, or the next day. You see how's the CPU is doing, how's the memory it is there anything, any regression that we introduced, if there's anything that can be worth investigating and doing. And then the team, as the team evolved, we started to have more discussion around how we can reduce the or how we can optimize such function, how we can reduce the memory it needs for this function, and then go back to the cost-saving discussion. So we talked about proactive troubleshooting, reduced downtime, a better resource utilization. Reduced downtime, again, it's similar to what we said in better feedback loop. We are more into proactive analysis rather than being reactive. so we catch, hopefully, the bugs and regressions before they become outages, so the downtime is actually reduced. Improved application performance because we have with the flame chart graphs, the flame charts, we can spot where the latency or where the bottleneck actually is and try to ask questions. Is this right? Is this method needs all that amount of time and actually to execute? And then finally, the performance regression detection, and that's what we're talking about when we talk about state. It's actually comparing the previous version and this version and understanding the bottlenecks and what actually changed and what issues the new version brought compared to the previous version. How we can acquire profiles. And for that, there are two. I already mentioned them, but going deep into it now. Either language-specific profilers. For Java, there's GDK Flight Recorder and Async Profiler. GDK Flight Recorder, I believe Anna has a workshop and a full good session about Flight Recorder, why it matters, how you can use it. And most of the tools that I will show afterwards support Java Flight Recorder. It's kind of becoming of the standard of profiling. But you can leverage it in your Java application to use it. If you are using other applications, Go has pproof, Rust has RB Spy, Python has cprofile, but each language has its own profiling tool that you can use to acquire language-specific profiling. And then in SafePoint, so let me start with what SafePoint basically is. When you're running your Java application, the JIT compiler adds what we call SafePoint, and basically checkpoints in your application that tells the JVM that it's actually safe to run your function, be it stack thread, be it garbage collection, or whatever. And that's because the JVM needs to perform some work, and that work, it needs to guarantee that it's the only one running at that time with nobody else running or intervening, basically. And that's what we call SafePoint. So basically, SafePoint are memory checkpoints. That's the JIT compiler adds in your code to tell the JVM that it's safe to do your work, and it's basically evolves some stop the world kind of scenario. And up until recently, this is what we call the SafePoint bias was an issue. And there's a good blog if you want to go deep into understanding why it was an issue. And the title is a little bit aggressive, but it was a big issue because of all of the profiling. GDK Flight Recorder and Async Profiler, the tool I've shown here, doesn't suffer from SafePoint bias, but I thought it's worth understanding what SafePoint bias actually is. So SafePoint is those points like this. Like each method, each code you wrote, the JIT compiler adds what we call the checkpoints. And then when you run an application, you want the sampling profile, or you want the profile, it's the grain lines, the grain arrows in there. So in ideal world, you will get the information that is running in the grain information. But since we cannot get the profiling information until the JVM reaches a safe point, this collection is delayed until we get the safe point. So rather than we get the information at the exact moment we want it, we delayed it until we reached the safe point. And then, because most of the profiling were using what we call the stack trace info. And that's, to get the stack trace information from the JVM, we needed to reach a safe point, because it's a safe point operation. The JVM needs to reach a safe point before it releases the stack trace. So when we reach it, and then we get the information. Now, it's not bad from the first part of the diagram, right? Because, yeah, we're still getting at least the method that we wanted. But think about the other one. There's no safe point because of some optimization whatsoever. Instead of getting, actually, imagine there is an arrow going down to the question mark box. We will not get that information, but we rather would get the server do next info. So we're lacking a view of what's actually happening. And the issue gets even worse with the aligning. The compiler does a lot of aligning for performance optimization stuff. It makes the compiler, it makes your application runs faster. It aligns everything into a single code. So all that gets collapsed and being part of service do something method. And all the grain arrows or the sampling or the profiling information that we wanted to get now get delayed until the service do something. So instead of getting detailed information of what's actually happening, we get the save point information, which is actually give us a wrong view and about what's happening in your application. That's basically what save point is, why it was an issue, why all profiling, especially in the Java world, we're facing it and suffering from it because it causes a lot of issue and give wrong view of what is actually happening. Again, GDK flight recorder and async provider doesn't suffer from it. So there are better tools in order to, doesn't suffer from the save point bias. So there are better tools to use in the future. Another way to acquire profiling, and that's probably what excites me about this whole presentation, is eBPF. How many of you are aware of eBPF? Okay, one person. Thanks, Tiffany. So eBPF is kind of a new cool tool, a new cool thing within the cloud-native world, cloud-native ecosystem, basically. Think of it as a way to make the Linux kernel programmable. Previously, if you wanted to do something with the Linux kernel, you need to go to the Linux kernel and change it, and then propose the changes to the Linux community to get it mainstream, or you end up maintaining your own version of the Linux kernel. And that sucks. eBPF is a way to make the Linux kernel programmable while using mainstream Linux kernel and adding programs that interact directly with the Linux kernel. So there are programs that get executed in the kernel space and not in the user space, which is really cool. I have a whole presentation about it. There are a lot of presentations out there. It's really cool if you're interested in the cloud-native world. I believe it's the future and will change a lot of monitoring and observability tools that we use because it executes within the Linux kernel. It's super fast, and it has a low overhead in terms of resources, obviously. So how it gets, it's different than the way we develop the programs that we use. The programs that we use with Java, Go, Rust, whatever, get executed in the user space. This one, or eBPF program, gets executed in the kernel space. And for that, we need some some trust in the code that we put in the kernel space. That's why it needs a lot of validation. So you develop your code, your eBPF program, with your favorite programming language. Not your favorite programming language. There are two languages that are supported, either C or Rust, C or C++ or Rust. Those are the languages that you can use to write the kernel code. You can write a user space code, but that can be with whatever language you want. So you write your eBPF program, you compile it, and it's compiled into bytecode. Even with Rust or C, it's compiled into bytecode. And why is that? It's kind of an intermediate level, similar to Java, before loading it into the Linux kernel. And then when we compile the program, we can load it into the kernel. But before it gets loaded to the kernel part, there is a verifier that makes sure that the code is actually safe to run. And there's a lot of discussion that eBPF programs are on Turing complete and whatever, but that's because it needs to run through the verifier. The verifier makes sure that every execution path in your program is actually reaching an end. So you can't have a while true loop, for example, in your eBPF program, because that will keep running and that will crash your kernel program. Traditional or compilers we use will just ignore it, because like, yeah, you know what, it assumes you know what you're doing, but the verifier, because it gets into the kernel, it makes sure that everything is actually safe to run. If you work with eBPF program, the verifier will give you a lot of headaches, but it is safe. It makes the code that we run in the kernel a lot more safe. If it passes the verifier, then we load it to the JIT compiler. And JIT compiler basically takes the bytecode and compile it into native code, and that native code gets attached to the kernel space. So your program is actually running side by side with the kernel, and it has access to everything. Whatever the kernel has access to, you have access to that. That's where the magic actually happens. You can monitor your processes, how they're running. You can monitor the network, storage, CPU, whatever. But then you can offload some of the functionalities to the hardware. It needs to be eBPF-enabled hardware, but you can, for some network functionalities, you can process them before even they reach the kernel. And that's really fast. Cilium is one of the tools that does that. It has a kind of service mesh, kind of, but it's a networking tool. It can be offloaded to network-capable card, and then it can filter the requests before even it reaches the kernel. So it's a program that is running in the hardware, which is super fast. And the same thing for the storage. So basically, you have visibility over everything that the Linux kernel has access to, which is everything. And then the program runs with a very low overhead and super fast. And if you still remember the rings in the operating system, it runs within the inner rings. So that was a very quick, very shallow introduction to eBPF, but it's a very cool. Make sure to check it out. I believe it's very cool, and it's going to change how we think about a lot of tools, especially monitoring and profiling one. Open source tools that are based on eBPF. I'm going to talk about 3 that are most known. So Pixie from CNCF, my favorite one. It does more than continuous profiling. It's a whole monitoring suite, kind of. We'll get into that. Periscope from Grafana, and then we'll have Parka. And you can see that they are starting to gain a lot of momentum, a lot of popularity recently, as continuous profiling getting a lot of attention, and as eBPF is growing. Parka is eBPF based. It can be run in Linux node or in Kubernetes environment. It has low overhead thanks to eBPF. Its architecture is very inspired by Prometheus, and we will get that in a minute. And it has a REST API, which makes it really cool to interact with either your application, your CI/CD tools, your monitoring tools, and so on. And it has a good security-related considerations. It's an open community. Everything they do is available and open, and it's really cool. And they have consideration, security consideration in their mind. So the architecture, if you are familiar with Prometheus architectures, service discovery and such, it rings a bell as well. But you have an agent, the Parka agent, or you can design your own one with whatever profiler you have in your code and send it there. And then it's as any profiling information or profiling tool that we mentioned, then the profiler will basically analyze it and they'll store it somewhere. And then we have an object storage that we use, and then we have a visualizer, and so web UI plugin. Periscope. So Periscope is from Grafana. It takes the most of both worlds. It supports eBPF and it supports agent-specific profilers. It has Java with JDK Flight Recorder, Go, Rust, and so on. It has a long-term storage. They claim it's efficient, but that's for you to test. That supports all the blob storage, be it S3, Google Cloud Storage, and so on. It has support for multiple languages, as I mentioned, and it also supports multi-tenant. Periscope is very enterprisey, if you think about it. If you want eBPF, easy to set up, you go with it. If you want language-specific, you can have it. So it's cool. Its architecture, again, similar to other things or other continuous profiling tool. Specific agent profiles or eBPF that can go there. You can develop your own, insert it, instrument it in your code, and send it to the profiles. And then it has a storage that basically stores the information, and then a server with a UI that analyzes it and provides visualization. And my favorite one, Pixie, from New Relic. It's a CNCF sandbox project. It's more than a continuous profiling tool, but that's part of it. It's an observability platform. It doesn't store information. It doesn't have a storage way, or a storage unit in it. It stores the information basically in your nodes. And it's keep them there. They said like it's a low overhead, but that's something to try out and see. And it has Pixie's native scripting language, PixieL, and that will basically enable you to query the language. It's kind of their own DSL of querying Pixie, and you can write program about it and then send it to in the search bar in order to get information. Wow, that graph looks super ugly. Wow, sorry for that. But so basically, we have the Edge. What is that? Edge Manager. Yeah, the Edge module. It's basically the tool that is installed in each node, and then we have the visor that's collecting the information. So Edge Manager, it's installed for each node. You're running Pixie on. Visor installed within the cluster. It's the collector because it doesn't store anything. Everything is still within the node, and then it sends the information to the Pixie API or to Pixie Cloud. A Pixie Cloud simply manages authentication or authorization and who gets access to what. And then we have Pixie API that serves both the UI and serves the CLI. So you can interact with them with both ways. I have a small demo that I wanted to show. Can you see that? So basically, I have a small application that is a ride-sharing application. So it's running, and then I'm using Periscope. So I'm creating a label by region, and then a region is in Docker Compose. So I have 3 regions. I have EU North, EP, Asia South, and then US East, right? And then I have an order service. It's basically that take orders from vehicles. And then I have 3 types of vehicles. It's like, think of it an Uber, but it's a small scale. So I have a bike, I have a car, and I have a scooter, right? So I'm running an application, and I have in a Docker load generator, that's the script. Basically, send the application or load my application with a lot of requests. Hello? Yes. And then I have, yeah, maybe. So I have Periscope, which is the information about the Periscope that's running, and then I have my ride-sharing app, which is actually this one. Maybe I can just focus on the flame graph chart, and you can see that my application is actually running, and I have the flame chart graph over the thing that are running. There's an issue in that, in the process, and you can see that the CPU actually is spiking. So if I select the bike, you can see that the CPU is actually lowering. So that's weird. If I select, what's the other one? Yeah, the car is where the issue is. Scooter, yeah. CPU is relatively less, and then if I fix the car, you can see that the car is actually spiking. So there's an issue in the car path. The second thing I want to do is to check which region is actually suffering from. Check up north. It looks less compared to, for example, EU what? East, thank you. East, is that right? Nope. That's fine. Can execute it back again. Go, check the region, and then EU North, yes. You can see that the issue is persistent. So I know that the issue is actually in the car path in the EU North region. I have this diff view, which is really good. So it allows me to compare 2 versions of my app running side by side. So I have the vehicle is a car. I'm interested in that because I know that's where it's actually happening. I want to compare the EU North with non-EU North region. So if I execute it, you can see that I have 2, I'm not sure if you can see that. I have 2 colors. One is the EU North and one is non-EU North. And you can compare it side by side. And you can see that EU North, the CPU is spiking compared to the non-EU North. I have the flame chart graph, which is basically showing what's eating all my CPU. You can see that it's actually similar, 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 until I came to this one. You can see that, oh, the check driver availability is what's eating most of that, and then going into much more details. So if I go to that, order service, check drivability, that's method. And you can see, if you're reading the code, you can see that I explicitly added kind of delay. Mutex logs basically add some delay to the function. So for the EU region, I'm inserting some delay. Just to show that if there is a bottleneck, something that's causing that, probably continuous profiling will help to understand why actually is causing it. I think I'm running out of time, so I have 2 other slides to share. First one is, I expressed already my enthusiasm about eBPF and how probably good it will be. So I believe that eBPF will see it more and more into more continuous profiling tool and more observability and monitoring tool because of the big ecosystem it's trying to have and also the low overhead that it's providing. So it's going to be more and more, you're going to hear more and more about it in the observability stack. And then OpenTelemetry are doing great work in adding support for profiling. So soon it's going to be added to the, all the stacks that OpenTelemetry is actually supporting, which is really good. Thank you very much. That was all.